Hey everyone, Mr. Hauk here. In today's video, we're going to be using oblique triangles to solve application problems. Let's get started. So throughout these application problems, we're going to be using the law of sines, the law of cosines, and the area of oblique triangles. In this first problem, on a baseball field, on a regulation baseball field, 4 bases form a square whose sides are 90 feet long. The center of the pitching mound is 60.5 feet from home plate. How far is the mound from first base? So we were fortunate enough to get a picture with this problem. And I'm going to go ahead and just make a couple notes here. Here's home plate. Here's the pitching mound. Here's first base. Kind of imagine something like that, okay? So what we're trying to figure out is how far the mound is, the pitching mound, from first base over here, which is just this side D. Now when we look at the triangle, notice we have a side, an angle, and a side. And this tells us, since we have side angle side, that we need to use the law of cosines to find this side length D. So side angle side, use the law of cosines. Setting up the law of cosines, I'm going to set it up as this side D squared is equal to 60.5 squared plus 90 squared minus 2 times 60.5 times 90 times the cosine of 45 degrees squared. Since we want to find what D is going to be, we're going to take the square root of both sides, and that tells us that D, the distance from the pitching mound to first base, is about 63.72 feet. Here in our second example, to determine the distance across a lake, AB, a surveyor goes to point C where they can measure the distance from C to A and from C to B, as well as the angle ACB. So this is what we're trying to find. We're trying to find this distance, AB, across the lake. This is that point C that they're talking about that the surveyor goes out to. So if the surveyor measures that the distance from A to C is 865 feet, and the distance from B to C is 188 feet, and that this angle in the middle is 42 degrees, then we want to know how far is the distance across the lake. How far is that distance AB? So again, looking at what we have, this is very similar to the problem we just looked at. We have a side, angle, side, and we're trying to find this side across from the angle. So that tells us that we're going to use the law of cosines again. So once again, plugging in the pieces, this side, x squared, equals these two sides squared and added together, minus 2 times these two sides, times the cosine of this included angle, take the square root of both sides, and we get that this distance, AB, is about 736.12 feet. So both of these examples here on the front page of the notes are both law of cosines application problem examples. All right, here in our next example, circular tracts of land with diameters 900 meters, 700 meters, and 600 meters are tangent to each other externally. There are houses directly in the center of each circle. You can see those houses right here. What is the area of the triangle connecting the houses? So this is a pretty interesting problem. Notice it's saying that we have these circular tracts of land with diameters of 900 meters, 700 meters, and 600 meters. So the diameter of the bigger circular tract of land is 900. And remember, diameter goes all the way through the circle, through the center. Well, that means that this little part of the triangle is going to be half of that diameter, or the radius. So we know that for each of these little pieces, we want the radii of these individual circles. So I calculated them right up here. The radius, if one of the diameters is 900 meters, the radius of the bigger circle is 450. The radius of the kind of the middle circle will be 350. And the radius of the smaller circle will be 300. And here you can see in my image, I went ahead and labeled all those. We know that both of these distances are going to be the radius of this big circle, 450. Both of these distances will be the radius of the middle circle, 350. And both of these distances will be the radius of the smaller circle, which is 300. And what we're going to do is we're going to just take this triangle and single it out. Notice if I add these sides, 450 plus 350 is 800. 350 plus 300 is 650, and 450 plus 300 is 750. And notice that this is a side-side-side triangle, and we actually just learned that when we have a side-side-side triangle and we want to calculate the area of this triangle, that we can use Heron's formula. Okay? So to calculate, or to use Heron's formula to calculate the area, we need to find the semi-perimeter. Remember, the semi-perimeter is the perimeter cut in half. So we're just going to add up all these distances around the triangle, 750 plus 800 plus 650, and we're going to cut it in half. That's going to give us a semi-perimeter of 1100. Plugging that into Heron's formula, this is going to give us the area of the circular, or this triangle rather, in the middle of these circular plots of land. And that's going to give us the area is 227,980.26 meters squared. It's a pretty cool problem there. All right, for our last problem here on the application notes, two markers A and B are on the same side of a river and are 58 feet apart. So that's right here. Two markers A and B, 58 feet apart. A third marker is located across the river at point C, right there. A surveyor determines the measure of angle CAB is 68 degrees. Remember from geometry that when we have angles written this way, you're really looking at that middle letter right there. So this is saying angle A is 68 degrees, and you're tracing from C to A to B, and that angle in the middle. Then we also have measure of angle ABC is 52 degrees. So A to B to C, those are 52 degrees. We will know how far is the distance across the river, which is this distance D. Okay, a couple things to notice here in our picture. They gave us the 68 degrees and the 52 degrees. They also gave us the 60 degrees. And we of course know that the angles of a triangle add up to 180 degrees. Now what I decided to do real quick is to go ahead and calculate this angle right here. We know that this is a 90-degree angle. So 90 degrees minus the 68 degrees here gave us the 22 degrees right there. Okay, so let's kind of think strategy. We want to find this distance D that goes across the river. And in order to do that, what we're actually going to do is we're going to find this distance B that goes from A to C, because once I have B, and knowing that this triangle is a right triangle that I have highlighted there in the laser color, well then we can use SOHCAHTOA to find this distance D. So first order of business, let's find B, this length of this triangle. And when I look at this, I'm going to use the law of sines. I have an angle, a side, and an angle, and I can use law of sines pretty quickly and easily. So let's find B. I'm going to set up the sine of 52 degrees over side B equals the sine of 60 degrees over 58. Cross multiply and solve for B, and you're going to get that B is 52.78 feet. Now that I know that this is 52.78 feet, then I can use SOHCAHTOA, or our right triangle trigonometry, to find the side D. So notice that the cosine of 22 degrees, this angle right here, well, we know cosine is the adjacent leg, which is D, divided by the hypotenuse, which is B. And notice I'm looking at this little right triangle right here. So the cosine of 22 degrees is D divided by 52.78. If I multiplied both sides by 52.78, I would get that D, the distance we're looking for, the distance across the river, is 52.78 cosine of 22 degrees, which is 48.94 feet.